I think the circuit would be very, very important. So we have two resistors connected in parallel. Those two resistors in parallel are also in series with another one. Okay, so these are the two connected in parallel, and it is in turn in series with another one. This is the source of EMF with an internal resistance R. I think this is 3 ohm, 3 ohm. Then the other resistor is 6 ohm. It is also in series with an 8 ohm resistor. And we are told that the current flowing through the 6 ohm resistor is 0.2. And we are to determine this is 12 volts with internal resistance R, which is unknown. And we are actually tasked to calculate for. So now, one thing we must understand is that when resistors are connected in parallel, they have the same voltage across all of them. So the voltage drop across this will be equal to the voltage drop across this, or potential difference. And this is because they are connected in parallel. So that's the first thing you must understand and apply. That when resistors are connected in parallel, you have the same PD. So once we have the resistance of this resistor, we have the current. Using Ohm's law, we can calculate for the PD, or the voltage across it, okay? And that would be, of course, Ohm's law is this. So the PD across the 6 ohm resistor will be 0.2 times 6, which is 1.2 volts. Okay. And this is also the voltage across the 3 ohm resistor, because those two resistors are in parallel to one another. Therefore, we can easily also find the current through the 3 ohm resistor. So current through the 3 ohm resistor would be equal to the voltage divided by the resistance, which is 1.2 divided by 3. And this is equal to 0.4 ampere. Okay. Now from Kirchhoff's current law, the total current at a junction, Kirchhoff's current law says that at a junction, total current entering the junction is equal to the total current leaving that same junction. Okay, so the current through the 3 ohm, through the 6 ohm are leaving this junction, J. They are leaving this junction, J. And the total current leaving the junction must be equal to the total current entering that same junction. And so we can say that the current from the source, I, which is entering this junction, J, would be equal to 0.2 plus 0.4. Meaning that the total current at that junction is 0.6 ampere. So this is the current from the source. Okay. Now, 0.6 current will divide into 0.4 and 0.2. Then they will combine again to leave this junction. Let's call this junction D. So 0.4, 0.2 would enter this junction, and that is the sum of it will be the same current leaving the junction D, meaning that the current that will flow through the 8 ohm resistor would be this. If we have the current, then we can also find the potential difference across the 8 ohm resistor. So V8 ohm will be equal to the current, which is 0.6 times the resistance, which is 8. Now, what is 0.6 times 0.6 times 8? What is 0.6 times 8? Of course, that would be 4.8. Please, are you there?
Yes.
That would be 4.8 volts. Now, Kirchhoff's current law. You see, here we are giving the internal resistance. If we are not giving the internal resistance, then we can just sum up the PD across the parallel, the series to be equal to this. But because there is an internal resistance, whenever current flows through it, there will be voltage drop by the internal resistance. This is what we term as the lost volt. So the EMF must be equal to the PD across the external resistance, which is the terminal voltage, plus the voltage drop across the internal resistance, which is the lost volt. Now we found the PD across the parallel circuit, that is 1.2. The PD across the 8 ohm resistor, which is 4.8. Meaning that the total voltage, the total terminal voltage will be equal to 1.2 plus 4.8. And this would be equal to 6 volts. Okay, so the terminal potential difference or terminal voltage is equal to 6 volts. Once we have the terminal potential difference, we can find the lost volt. The lost volt, small v, would be equal to EMF minus the terminal potential difference, which is 12 minus 6, giving us 6 volts. And once we have the lost volt, we can easily determine the internal resistance of the battery, because the same magnitude of current I will flow through, will flow back from the battery and enter, re-enter the same battery. Okay, so once we have the lost volt small v is equal to I times small r. Small v is 6, I is 0.6, and then the internal resistance is this. Therefore, we have 6 divided by 0.6, which is 10 ohm. Please, if you have any question, you can quickly ask before we continue. If you have any question on what we've done so far, ask. Or can I continue? Ravana, Bella,
Yes,
Kenneth.
please.
Okay. All right. So we found the lost volts. In fact, the I question demands that we find the internal resistance. And the I is the terminal potential difference, which we've already found, determined. Okay. So we have 6 volts. Another approach of finding the same thing can be, let's find the total external resistance. 1 over R total is equal to, this is 1 over 3 plus 1 over 6. And that will be in series with the 8 ohm resistor. When we sum this up, this is 2. This is 2 ohm plus 8. Therefore, our total will give us 10 ohm. Then the terminal voltage, which is I times R total, will be equal to 0.6 times 10. And this is 10 volts. I'm sorry, this is 6 volts. 6 volts. 6 volts, the same as what if earlier had. Okay. So this is the solution to the question. Rabna, are you okay?
Yes, sir.
All right. Let's quickly look at how to cost. Okay, before we do that, let's talk about Kirchhoff's law. Then we can talk about how to cost electricity. Okay. Kirchhoff's law. We applied Kirchhoff's law in solving this question. And so I made mention of the current law, the voltage law. But the question is that what is Kirchhoff's law? How is it used? And how is it different from series parallel circuit arrangement? One, Kirchhoff's law is used for solving complex electrical circuits. It is used to solve complex electrical circuits. When do we have a complex circuit, and when do we have less complex circuits? You see, if I give you a combined circuit, an example of what we just analyzed, these are 2 resistors in parallel. They are also in series with another one. I can choose to add other circuits or resistors arranged in different forms, such as this one. No matter how giant the circuit may look, if the source of EMF is 1, it is not a complex circuit. So I can add on other resistors in series or whatever. So long as the source of EMF is just 1, the circuit is less complex. So we talk about complex circuits when we usually have 2 or more sources of EMFs. Okay, so when we have 2 or more sources of EMFs, the circuit becomes complex, no matter how simple or elaborate the circuit may look like. So Kirchhoff's law is used for solving complex circuits. Okay. Let's go through the laws. Gustav Kirchhoff gave us 2 key laws. So we have Kirchhoff's current law. Kirchhoff's current law. Then the second one is the voltage law. Kirchhoff's voltage law. Kirchhoff's current law is what was stated earlier, that whenever you have a circuit and there's a junction, and in physics or electrical systems, a junction is a point where three or more wires or conductors connect. So I'm drawing three resistors and then connecting them in parallel to a source of EMF. Okay, current conventionally moves from the positive terminal and enters the negative terminal. So when the current flow gets to this point, and look at this point, we have 1, 2, 3, 4 wires joining or interconnecting. Automatically, at this point, creates a junction. A junction is a point where more than two wires interconnect. Okay, so it means there is another junction here because we have 1, 2, 3, 4 wires. E. So we have junction D and E. Kirchhoff is saying that the total current entering a junction must be equal to the total current leaving that same junction. So supposing the current through R1 is I1, and then through R2 is I2, then through R3 is I3. Kirchhoff is saying that I must be equal to I1 plus I2 plus I3. This is Kirchhoff's current law. The condition for application of Kirchhoff's current law is that there must be a junction. So the condition for this to be applied is that there must be a junction. If there is no junction, you cannot apply Kirchhoff's current law. Class, are we okay?
Yes.
Kirchhoff's current law is a statement of conservation of charges. So the current law is a statement of conservation of charges. It's a statement of conservation of charges. And that is, total charges entering a junction must be equal to the total charges leaving that same junction. Okay. Current I is equal to Q over T. So I1 would be equal to Q1 over T. You can say T1 or T. I2 is also equal to Q2 over T. Then I3 is equal to Q3 over T. If we equate, Kirchhoff is saying that I is equal to I1 plus I2 plus I3 at a junction. So I, which is Q on T, is equal to Q1 on T plus Q2 on T plus Q3 on T. Now, the time taken for the flow of charges. Charges move or flow at the speed of light. So they take they travel at the same time. So T at the source, T entering to as charges flowing to each of the resistors the same. Therefore, the time will cancel out. So we have Q is equal to Q1 plus Q2 plus Q3. We have derived summation of charges, leaving the junction to charges entering that same junction from the current individual current equation, confirming the fact that Kirchhoff's current law is a statement of conservation of charges. And the condition for its application is that there must be a junction. All right, let's look at the voltage law. Kirchhoff's voltage law. The voltage law is also a statement of conservation of energy. And the condition for its application is that there must be a closed circuit. So let's have loads connected in series or in parallel. These are three loads or resistors: R1, R2, R3. Connect them to a source of EMF, which can be a battery such as dry, wet button cell, or a generator. For current electricity, let's use battery V. Kirchhoff is saying that once you have a closed circuit, and don't forget, a closed circuit is one of the conditions required for current to flow. So Kirchhoff is saying that if you have a closed circuit, the potential difference across all loads or resistors within the closed circuits, when you sum up all the PDs across the resistors or the loads within the closed circuit, it must be equal to the source PD. So V, the source PD is V, and Kirchhoff is saying that if you have a closed circuit, then the PD across all the sources, V2 plus V3. And that's what happens when there is a closed circuit. So the condition for application of Kirchhoff's current law is that there must be a closed circuit. And the law actually says that in a closed circuit, the potential difference across, or the sum of potential difference across all resistors must be equal to the source potential difference. Please, if you are writing, state it or write it as how I'm giving you. In a closed circuit, the sum of potential difference across all resistors or loads must be equal to the source potential difference. This is similar to the distribution of, we sometimes connect water, the distribution of water to current. Water itself is the current. The pipeline within which the water flows is akin to resistance. Then the voltage is the pressure which pumps the water through the pipe. If this is a Kirrchhof house, V1, this is R2 is a Kirrchhof house, and R3 is Bella your house, if we have a closed circuit, if there is no leakage within the pipe, then the volume of water coming to your house plus volume of water coming to Ekuya Watman's house and then Ekuya Adome's house must be equal to the source, the volume of water pumped from the source. Okay. If there is leakage somewhere, which is once there is leakage, it means the circuit is open. There will be outflow of water. So once there is leakage somewhere, I cannot say that what is coming to your homes is equal to what is being pumped. No. Okay. So we can relate Kirchhoff's second law to this, that within a closed circuit, the sum of potential difference across all resistors must be equal to the source potential difference or source voltage. And Kirchhoff's voltage law is also a statement of conservation of energy. Kirchhoff's voltage law is a statement of conservation of energy. Please, if you have any question, quickly ask. Colonel,
Sir,
any question?
no, please.
Okay. All right. Let's go into how to apply Kirchhoff's law in solving problems. As I indicated earlier, Kirchhoff's law is used to solve complex circuit problems. And the circuit is complex when there are two or more sources of EMFs. Okay, so I'm going to draw a circuit with two EMFs. So we have a resistor 1, the source of EMF E1, this is R1, R2, so we have R1, R2, R3, this is R4, this is E2. Okay, so this is a complex circuit because we have two sources of EMFs, E1 and E2. If we have only one source of EMF, assuming this is what we have, then there's no need of us applying Kirchhoff's law in solving this problem, meaning this is not complex. This is because if the circuit is like this, R3 and R4 are in series, and we can easily combine them to be one resistor. Okay. I just want to introduce a quick sketch if we have that situation. So a single resistor R2 because we can combine R3 and R4, they'll combine to give us one resistor or resistance. Let's call this R total. Total because we've combined 3 and then 4. This is R2. This is R1. Now, because there are junctions here, okay, it's obvious R2 and R1. R2 and RT are also in parallel. We can find their equivalent resistor, and that equivalent resistor would then be in series with R1. So R equivalence, which is the combined effect of R2 and R, will just look like this. And this will be in series with this, and we can easily look for whatever we are looking for. So if there are no, if there is only one source of EMF, we do not use Kirchhoff's law. You can use it, but when you use it, it's a waste of precious time. Is that okay? If you use it, it's a waste of precious time, because with Kirchhoff's law, you must obtain equations, solve them simultaneously. So if the question is not complex, just use parallel series combination and you are good to go. Do not waste your time unless the question as it was framed requires that or restricts you to applying Kirchhoff's law. But if you are not restricted, do not waste your time. Okay, so this is what we have. So how do I apply Kirchhoff's law? 1, assign direction of current to the circuit. Please write it for me. We are going through the methods, how to apply Kirchhoff's law. So 1, assign direction of current flow. So if the question is such that direction of current hasn't been assigned, then 1, you must assign direction of current flow within the circuit. Within the circuit. Meaning that if the circuit is such that direction of current has been assigned, you must work with what you are given. You cannot change the direction of current assigned. But if the question is such that you are to assign direction of current flow, then you must do so. In doing that, how do I go about it? Conventionally, current flows from positive to negative, and electrons also flow from negative to positive. So I will always want to follow conventional directional flow of current. Once I have that opportunity to assign direction, okay, to the flow of current. So the current produced by this source of EMF, I am representing that by I1, and I'm following the conventional directional flow of current from the positive to the will flow or move and then enter into the negative. Then this source of EMF would also drive current or charges through the circuit. Okay, and when charges flow, it creates current. So I want to obey conventional directional flow of current. And this is also I2. Please note that the current assignment of directional flow of current can also be from the negative to positive. But when you have the chance to assign directional flow of current, you must always go the easy way from positive to negative, unless the question is such that it's been given to you, and so you must work with what has been given to you. Please, are you okay? Hello, are you there? Or you are asleep?
Sir, please, you are here.
Okay, so I'm only following conventions. Okay, so after assigning direction, you see, I1 will get to this junction. I2 would also flow and get to the same junction. So at this junction, it's obvious I1 and I2 are currents entering that junction. Kirchhoff is saying that sum of current entering the junction must be equal to the sum of current leaving that same junction. So I want to denote the current leaving this junction by the letter I3. And so I can apply Kirchhoff's current law in an equation form here. That is, I3 is equal to I1 plus I2. This is equation 1. This is equation 1. Now you must choose the second method is that, so first we assign directions to the flow of current. Then 2, we have applied a junction rule. So assign direction flow to current, and 2, apply the junction rule. The third method is that derive as many loops as you can, or obtain as many loops as you can from the circuit. So let's actually label our diagram. Okay, we want to label the diagram using the vertices. This point A, B, C, D, E, F. So choose as many loops as possible and solve them simultaneously. So I'm going to choose loops, okay, closed circuits, or this is closed circuits or loops. Now, you can choose your loops or your closed circuits as you go clockwise or counterclockwise, what we famously call as anti-clockwise, clockwise in the clockwise direction or anti-clockwise direction in choosing our loops. So the choice is actually yours. So I will want to go clockwise. You may also choose to go anti-clockwise. So this is the direction of my choosing loop. I'm moving clockwise. So considering the loop, I'm going clockwise. So A, B, E, F, back to A. Please, if you start from a vertex and you don't end there, it is an open circuit. So if I want to go clockwise, then I want to start from this vertex or point, considering the loop or the closed circuit A, B, E, F, I must end at A to close the circuit. I can also pick the same loop by B, E, F, A, B. So long as it is clockwise, you haven't violated any rule. Okay? So long as you are moving clockwise, you haven't violated any rule. It can also be E, F, A, B, E. So that's it. Considering the loop A, B, E, F, A. Now, when the direction of the loop, please listen to this point. When the direction of your chosen loop, when the direction of the chosen loop is from the positive terminal of the loop, is from the positive terminal is from the positive terminal of the source of EMF to the negative terminal of the same source, the EMF is positive. When the direction of the chosen loop is from the positive terminal of the source of EMF and enters into the negative terminal, the EMF source is positive. And when it is the other way around, the EMF source is negative. So, will this source of EMF, E1, will E1 be positive or negative? Class. Will E1 be positive or negative?
That is positive.
So positive. So this will be plus E. This is because that my loop, the loop you picked, is from the positive terminal of the EMF and enters into the negative terminal. And if the loop, meaning that if we had gone anti-clockwise, this EMF would have been negative. Please take note of that. So positive EMF must be equal to, we are now coming to apply Kirchhoff's second law because we have a closed circuit. Now, Kirchhoff's second law is saying that within a closed circuit, the PD across all resistors, the sum of PD across all resistors must be equal to the source voltage or potential difference. So I equate this to the PD across this one. Okay. Now look at my loop A, B, E, F, A. The moment you pick a loop, it is like cutting out these ones. So your focus is only on your loop. All other resistors do not count here. So the moment you choose a loop, it is like truncating or cutting out all other circuits. It is as if the attention is only on this part. The other part does not exist. So the PD across this. Now listen to another rule. The PD across this resistor, the potential difference across a resistor is positive if the direction of the current flowing through that resistor follows the direction of the chosen loop. I take it again. The PD across a resistor is positive if the direction of current flowing through that resistor follows the direction of the chosen loop. So class, look at the PD across this resistor R1. Will it be positive or negative? Are you
Positive.
there? So it's positive. I'm taking it again. The PD across a resistor is positive if the direction of current flow through that resistor follows the direction of the chosen loop. And the PD across a resistor is negative if the direction of current through that resistor is against the direction of your loop. So per that rule, then the PD across R1 will be positive. So I1 times R1. The current I3 also flows through R2. Will the PD across it be positive or negative? Class. Will the PD be positive or negative? Hello, I'm listening. Oh,
Yeah, please, positive.
Positive. This is because the direction of the current follows the direction of the chosen loop. So plus I3 times R2. And this is equation 2. Okay, you must derive as many loops as you can and solve them simultaneously. So this is one. We must also have another loop. Equia,
Stadia.
what is happening to Equia Adoma? Okay, so let's choose another loop. I want to always go clockwise. So in my second loop, I want to follow the direction of the first loop. I want to go clockwise as well in this. Now, so as I said, the moment you pick a loop, it is as if you are cutting out the other side. So this side will never come in. The focus is only must be on this particular loop. So considering the loop, I want one of you to help me pick my loop. I'm going clockwise. So give me letter representation of the loop. Yes. Bella, help me choose a loop.
Stadia, please. B, C, D, E, B.
B, C, D, E, B. Thank you.
Okay.
B, C, D, E, B. Everyone, what is happening to your network? Now, class, the source of EMF, will that be positive or negative? Look at the loop and the polarity of the source of EMF. Will it be positive or negative?
Yeah, please, negative.
Please, do you all agree? that it will be negative. Epia, do you agree?
Yes, sir.
Ewurabna, do you also agree?
Yes, sir.
Okay, Bella,
Yeah.
do you agree or disagree?
Teacher, please, I disagree.
Bella, I agree. Okay,
You agree.
so let's look at the rule. If the direction of the loop is from the positive terminal and enters the negative terminal, then the EMF is positive. If the direction of the loop is from the negative terminal and enters the positive terminal, the EMF is negative. So we picked a clockwise loop. So when we follow, let's even follow from here. We are moving clockwise. Okay, so it's as if this loop is starting from the negative. This is the positive. This is the negative. Look at the direction of the current. Let's indicate that as we move on. So it is as if we pick it from here, it's as if the loop starts from the negative, goes on, and then enter into the positive. Bella, do you see it?
Teacher, can you please take it again?
So the rule is that if the direction of your chosen loop is from the positive terminal and enters the negative terminal, the EMF is positive. If it is from the negative terminal of the battery and enters into the positive, EMF is negative. We pick a clockwise loop. So when you look at this, when you follow the direction of our loop, let's use the arrow to just match the clockwise direction. You see, at this point, when you get to the positive terminal, the arrow is entering into the positive. When you pick it from the negative direction, the arrow seems to be coming from the negative. The negative is the shorter one. The positive is okay. So whichever direction you judge this from, the arrow seems to be moving from the negative and entering into the positive. Please, you see it?
Yes, please.
And so the EMF must be negative. So minus E2 must be equal to. Now look at the current flowing through the batteries. If we look at it from, we are moving clockwise. So let's follow the direction of this. The current I2, is what is produced by E2. It will go and then enter into the negative terminal. So it is I2 which is actually flowing through R4 because I2 will leave the positive, go and then come and enter through the negative. So I2 is what is actually flowing through R4. Now the PD across R4, would that be positive or negative? Class, over to you. The PD across R4, will it be positive or negative? Yes. Anybody?
Please, negative.
Why negative? Kenneth, why negative?
No, because the direction of flow of current is opposite
to the loop, to the
direction
direction
of
of the chosen loop. Thank you. So minus I2 times R4 because the direction of I2 is against the direction of the chosen loop. Okay. Let's also look at the PD across R3. And now, will that be positive or negative? The PD across R3. Will that be positive or negative?
It's negative.
Negative. The same reason, the direction of current I2 is against the direction of the loop. So minus I2 times R3. Then lastly, the PD across R2, would that be positive or negative?
It's negative.
Minus I times R2. Thank you. And so when we factorize out negatives at the right-hand side, we'll have E2 being equal to I2 times R4 plus I2 times R3 plus I times R2, because all the negatives will cancel out. Okay, so this is equation 3. Kenneth, ask your question.
There.
Hello.
Answer. So, considering the loop, could you have also made it B, E, D, C, B?
So Kenneth, you can go clockwise, you can go anti-clockwise. Whichever direction you want to go, you can. But do not forget to apply the rules. So I could have, gone anti-clockwise in the second loop and then in the first loop. So you are free to choose whichever loop you want to go, but you must understand the rules of the game and apply accordingly.
Mr. Dear.
Mr. Akuya.
So the first one, can you decide to choose anti-clockwise for the first one, and the second one you choose clockwise?
You can go whichever direction you want. You can go clockwise for the first one, you can go anti-clockwise for the second one. But at whichever direction you go, you must get the same results, answers.
Stay there.
Hello.
Because I don't understand why the current flowing through R4 is I2 and not I.
You see, originally we said that let the current produced by I2 be produced by E2 be I2, isn't it? When we were assigning the direction of currents. Okay. Are you okay?
Yes.
Meaning that I2 would go through separate into whichever component. But when it is returning back closed circuit, it must be I2. So this can be 10 ampere. When it gets here, it will break into this, if there is even a third loop. But when it is going and it is returning back to this portion, it must be I2. So long as you are saying that let the current supplied by E2 be I2. So when it is entering or returning, it must be the same amount as when it was leaving, so that energy or charges will be conserved. Okay, are you okay?
Yes, sir.
All right. Please, if you have any other question, ask. Then don't forget there is a third loop we can also look at. That's the bigger loop. We can also pick the bigger picture. That is, considering the loop ACDFE or AFDCA, whether you want to go clockwise or anti-clockwise. Okay, so we can also consider considering the loop AC because I want to go clockwise. ACDFA. And I told you, when you pick a loop, it is as if this part is eliminated. The middle part is gone. We are only focusing on the bigger picture. That's why I'm clearing whatever we have within the bigger loop. So here I'm going clockwise. A, C, D, A, C, D, F, E. I'm going clockwise. Okay. Now, per the loop, what will be the polarity of this? Would E1 be positive or negative? Don't forget, we have two sources of EMFs within this chosen loop. So would the EMF here be positive or negative, Bella? Hello, Bella, are you there?
Yes, please.
Considering this loop A, C, D, F, E. Don't forget, within this loop, we have two sources of EMFs, E1 and E2. Would the EMF of this, of E1, will it be positive or negative?
You said, yeah, please, positive.
Positive. Why? What's your reason?
Yeah, please, one, the direction of flow is according to the clockwise thing.
So the direction of the loop is from the positive terminal and enters into the negative terminal. Are you okay? So
Yes.
E1 is positive. Now, what about E2? Would E2 be positive or negative? Will E2 be positive or negative?
Yeah, please,
Bella, agree.
it will be negative.
It will be negative. So, because we have two sources of EMF, you judge each using the loop and then sum them up. So E1 plus E2 is negative, so minus E2. In effect, the EMF of the loop becomes E1 minus E2. This is what happens when you have two or more sources of EMFs within a chosen loop. Rabna, ask me a question.
So please, I don't have a question right now.
Okay. Kenneth, ask your question. So
Yeah, please. I don't have a question.
So if you have two sources of EMFs or more, this is how you use the loop to analyze each one, okay, each of the EMFs at a time and then sum all of them up. I know you have a question. Ask. Ebiadoma.
No, sir.
All right. So E1 minus E2, then you look at the PD across the resistance. Right now, will the PD across R1 be positive or negative?
Sir, please positive.
So I1 times R1. The PD across R3, would that be positive or negative?
Sir, please negative.
So minus I2 R3. The PD across R4, positive or negative?
Sir, please negative.
Minus I2 R4. Okay, so you just in actual fact, you just need two equations to solve them simultaneously. So it can be solving equation 2 and 3, 2 and 4, this one, or 3 and 4. So usually when we're able to use the loop rule to obtain two equations, we are good to go. We don't worry ourselves, but I'm teaching you. So I just want you to understand that there can be a third loop. Okay, so whichever two equations you pick and you solve, you must actually get the same answers. All right. Please note that this illustration is based on the fact that we consider the internal resistance of the batteries or the cells to be negligible, 0. If you are given the internal resistance of the battery, you must also consider the lost volts. So the volts that will be dropped by the internal resistance as well. Factor that into the circuit. But this is on the account that R is equal to 0. In Kirchhoff's law, sometimes your correct answers can be positive or negative. Correct answers can be positive or negative. If you solve a loop question and your answer current value is negative, it only means that the actual direction of current flow which you took is against what it must be. That is why I is negative, but it does not mean it is wrong. But if your I value is negative and it is right, okay, as the examiner's results or answer, it simply means that the actual direction is against what you took. That is basically what it means. Okay, if you have any question, ask before I give you a real problem so we can apply. Okay, so I'm giving you a real question. Did you call Abiabuatin?
Yes, sir.
What's the problem with her line?
Simply she's in class. She has left.
Yes.
Mr. Diapni, she said she's facing network problems.
It's not working. Okay, I'm recording, so. So this is R1. This is 10 ohm. This is 8 ohm resistor. Giving you a simple one first. Don't mind my resistors. They look ugly. No, don't mind them. So we have another source of EMF. And this is 12 volts. This is 8 volts. Internal resistance 0. This is R2. Then this is R3 of resistance 5 ohm. The question is that determine the current and the potential difference across the 8 ohm resistor. So you are calculating for the current in the 8 ohm resistor as well as the PD across it. Okay. So let's see how we can apply our rule. So rule 1, assign direction to the flow of current. So this source, each of the sources would produce current. Let's first label the circuit A, B, C, D, E, F. So first assign direction of current. I want to follow convention. So I can choose to go by this. All that I'm saying is that let the current produced by this be I1. Let the current by this be I2. And I want to go from a conventional directional flow of current from the positive to the negative. That's why I'm going down. meaning I can also decide to go up. When we finish, I'll pick that direction as well and see how that will work out. So I1 and I2 would are two currents entering the junction E, and this must be balanced by the current I3 leaving the same junction. And so straight away, we could state that from what we've done, we can state that I3 is equal to I1 plus I2, the current law. This is equation 1. Then choose as many loops as possible. Maybe I want to follow the direction of current flow. So in this, considering loop A, F, E, B, A. So considering the loop A, F, E, B, A, meaning I want to go anti-clockwise. You can choose to go clockwise. The choice is yours. Now, what is the polarity of the EMF source? Will that be positive or negative? Bella, will the EMF be positive or negative?
Sadia, please, which one? The EMF.
Yes. Considering the chosen loop A, F, E, B, A, will this EMF be positive or negative?
Please, it will be positive.
So 8 volts is equal to the PD across R1. Will that be positive or negative? Bella.
Sadia, please, it will be negative.
What's your reason?
Sadia, please.
Erabra, would that be positive? The PD across R1, would that be positive or negative?
Please, positive.
What's your reason?
Please, I chose positive because
If the direction of current flowing through the resistor follows the direction of your chosen loop, the PD across the resistor is positive. If the direction of current flowing through the resistor is against the direction of the chosen loop, the PD is negative. So Bella, would that be positive or negative?
Sadia, please, it will be positive.
Positive. So 10 times I1. I1 will leave the source, be divided into whatever, but when it is returning, it must be I1. Okay. Then plus the PD across R2 must also be positive because the direction of current follows the direction of the chosen loop. So plus 8I3 2 can go into the coefficient. So 4, 5, I1 plus 4, I3. However, I3 is equal to I1 plus I2. So in place of I3, I substitute I1 plus I2. 5 I1 plus 4 I1 plus 4 I2. Okay, are you there?
Yes, sir.
So we have 9 I1 plus 4 I2. This is equation 3. Then we pick another loop. How do you want me to go? Do I go clockwise this time or anti-clockwise?
Clockwise.
Clockwise.
Yeah.
So considering the loop, once I'm going clockwise, I can go D, E, B, C, D, or B, C, D. The most important thing is that move clockwise. Okay. Look at this source of EMF. Will this be positive or negative?
Positive.
Positive, because the direction of the loop is from the positive and enters the negative. So plus 12 is equal to the PD across R3. Would that be positive or negative? The PD across R3, would that be positive or negative?
Positive.
So 5 I2 plus 8 I3 plus 8 I3. Then I3 is I1 plus I2. So when we expand, we have 8 I1 plus 13 I2. And this is equation 4. So you solve equation 4 and equation 3 simultaneously. Do that for me. Help me solve equation 4 and equation 3 simultaneously to obtain I1 and I2. Start with.
13 I2. Eight.
I2. Are we through?
So,
What are your answers?
please, I1 is equal to 0.047.
0.047
Yes.
and I2
Is equal to 0.894.
0.894.
894.
Please, the rest of you must confirm. Let's confirm.
Yes,
Can I-
please.
Is that you? Did you get the same thing?
Yes, please.
Okay. Can I? Rabna,
Yes, please.
Please.
did you get the same thing? Okay. So once we have I1 and I2, we can find I3. And I3 is the sum of I1 and 2. Do that for me. So when you put the two together, what's your final answer?
Say there, please. 0.941.
0.941 ampere.
Yes, please.
So the current through the 8 ohm resistor is this, and then the voltage drop across it will be the current times the resistance, which is 8. So 0.941 times 8. Umbrella.
Say there, please. It's 7.58528.
528 volts.
Yes, please.
Now, I want us to pick the third loop, the bigger loop, considering the loop A. I want us to go clockwise. A, C, D, F, A. So if we are going clockwise, then the middle loop will not be here. So A, C, so it means we are going this direction. Okay. The PD across the 8 volts, will that be positive or negative? They are loop. The PD across the 8 volts, will that be positive or negative?
Negative.
So minus 8. The PD across the 12 volts, will that be positive or negative?
Positive.
Plus 12. So we have a net of 4. So 4 volts is equal to, we have assigned current flow. The PD across R3 will be positive because it follows the direction of the loop. So 5I2, then the PD across this. Would that be negative or positive?
Negative.
Pardon?
Negative.
So minus 10I1. Okay. So we have 4 is equal to 5I2 minus 10I1. This may be equation 5. Now, when we pick equation 5 and either equation 4 or 3, we must get the same answers we had. So pick equation 5 and any other equation, either 4 or 3, and then solve them simultaneously. Let's see. Start with. And I'm giving you, I think 5 minutes will do. Any of 4 and 3.
Please, you
Sir.
get the answer.
Stadium.
Hello, Kenneth.
Sir,
Mhm.
sir, please, I'm not getting the same answers for I1 and I2.
Which equation did you pick?
So I had the same equations you had for 4 and 3.
So you use equation what and what?
4 and 3.
Oh, but 4 and 3 we solved it together. And I think
Sir, please, I'm not getting those answers.
oh, what's the problem? You are not getting 0.047 and
No, please.
0.894. Okay,
No, sir.
okay, so the rest of you must work on, okay, what I've just assigned you whilst I attempt to the next issue. Okay, so in your case, you want us to solve 4 and 3, right? Kenneth, is
Yes.
that okay? So
Yes.
let's think of eliminating 1. Okay. What is if you multiply 9 by 8, 9, what is 9 times 8? Kenneth, I'm listening. Multiply 9 by 8. Kenneth, are you there? Hello. Hello, Kenneth. Hey, what's the problem? So if I multiply equation 4 by 9,
72.
you have 72 I1. Meaning we have multiplied equation 4 by 9. Okay. Okay, so plus 13 by 9. 13 multiplied by 9. This is 117 I2. Kenneth, are you there?
Yes, sir.
Then equation 3, let's multiply that by 8. So 8 by 4, that is 32.
Yes, sir.
Then 8 times 9, 72,
Yes, sir.
plus 8 times 4 again, 32, I2. So if this is a new equation, this is new equation, let's subtract equation, assuming this is equation P and then equation Y. Let's subtract equation Y from P. Okay, so 108 minus 32. We have 76. I1 will vanish. And then 117 minus 32. We have 85.
5.
I2. So I2 therefore will be 76 divided by 85. Then what is 76 divided by 85? This is 0.894 ampere. And that's exactly what they got for I2. So I think you perhaps did not look at it well.
Yes, sir. I found a mistake I made.
Okay. And
Thank you.
welcome. What about the tax I gave you? Bella and Rabna, what about the tax I gave to you? Using equation 5 and either 4 or 1, 4 or 3. Bella. Hello, hello. Rabna. Hello.
Sir, please, I had different answers.
Which equation did you use?
So I used 5
5 and
and 3.
Bella, what about 5 and 3?
Yes.
Bella, what about you?
Savior, please, I use 5 and 4.
What are your answers?
Sadia, please, I had 0.0474 I1 and then I2 0.894.
So they are the same answers.
Yes, please.
Okay, Abraham, you said you use equation 3. So let's see. 4 is equal to 9I1 plus 4I2 and 4 is equal to minus 10I1 plus 5I2. Adoma,
Stay here.
what were your answers? Did you get the same results?
Yes, sir.
So maybe Bella, Abraham, something went wrong somewhere. Okay, so let's multiply equation this by 10 and this by 9 so that we can eliminate I1. So this is 40 is equal to 90 I1 plus 40 I2. Then this is 36 is equal to minus 90 I1 plus 45 I2. Let's subtract this. This is equation Z and then V. Let's even add them. Let's add them. When we add equation Z and V, we have 85 I2. I1 will go to 0 is equal to 76. The value is the same as what we had. So I2 straight away will be 76 over 85. And what is 76 over 85? We have the same results. So, I think something went wrong somewhere. Okay. Hello, Abraham. So that's it. That's the beauty of what we are doing. So you can your task today is that change the loops, change the direction of the loops. If I took clockwise, take anti-clockwise in the other one, and then in the other two, and then apply the rules. Okay, no matter the direction of the loops, you must get the same results. That's the beauty of the game. Class, are we okay? Emmett,
Sir,
are you fine?
yes, please.
All right. So please get questions. We have about 9 minutes to go. Look for questions. But before you do that, pick the same question, reverse your directions. Okay. Let it go against what I actually took, and then apply the rules and solve it to see if you can get the same answers we have. Then you pick examples from books, then you try your hands at it. We'll continue once again tomorrow. Is that okay?
Yes, please.
Have a very good night and sound sleep to you.
You too, Miss Sadia.
Okay. Bye-bye.
Bye.
All right. Kenneth Martin, thank you for the applause. All right. Yeah, tomorrow.
You're welcome.
All right.